Florian, over to you.
Okay. Yeah, thank you very much for the nice introduction, and thank you for the opportunity, of course, also to give a talk in this nicely filled seminar, I must say. I think I think it's one of the most people I've spoken before so far, but everything will be nice. So I will be talking about, generalization of three star homomorphisms on ordinate spaces. First, I need to cover some preliminaries in order for you to understand what I actually mean by these homomorphisms and what these order-unit spaces are. So let me start very nicely with the introduction of ordered vector space. So an ordered vector space is simply a pair consisting of a real vector space, let's say X, and a cone K. And the cone is simply a subset which is closed under addition and closed under scalar multiplication with positive real numbers, and such that the intersection of the cone with minus the cone is single to zero. So we have like pointed convex cone systems. And whenever you have such an ordered vector space, you can define a partial order by saying that a vector x is less than or equal than a vector y if their difference y minus x is in K. You have to think about the cone as the set of all elements which are positive, so greater or equal than zero, and then you use this to define a partial order. And it turns out that this partial order becomes compatible with the vector space structure. Then there are some notions that we are going to need and some notation. The first one is we need to define, or we need to look at set of upper and lower bounds. Whenever we have a set A, then I denote by A, and then this U, superscript U, the set of all upper bounds of the set A, and by AL, I denote the set of all lower bounds. And and finally, there's also a special class of ordered vector spaces, and these are those ordered vector spaces which are, in addition, a lattice, meaning that for any two elements, I have a supremum. And these are called vector lattices or Riesz spaces, and there's a whole classic theory which deals with these Riesz spaces. However, today we are mainly interested in the ordered vector spaces or in ordered vector spaces which have some nice properties. We of course also have structure-preserved maps or linear maps on ordered vector spaces. The most important one are the positive linear maps. So these are maps which map the cone back into the cone, or in other words, they map any positive element to the positive element. And if the converse is also true in some sense, meaning that if the image is positive, then your pre-image must also be positive, then we call this map bipositive. And it turns out if your domain X is directed, so for any two elements you have a common upper bound, it turns out that the set of all positive linear maps is itself a cone. So you can endow your space of linear operators with this cone of positive linear maps, and this turns your operator space itself into an ordered vector space. Now, some motivation for the class of ordered vector spaces that I want to introduce to you now. So classically, most theory is done for these vector lattices. Vector lattices have the lattice structure is really, really nice and makes or enables for a really nice theory. However, even if you work for vector lattices, you quickly come into a situation where you lose the lattice structure. For example, if you have a linear subspace of a vector lattice, this might no longer be a vector lattice. So for example, classic vector lattice is the space of continuous functions, but the space of continuously differentiable functions fails to be a vector lattice. And another example happens when you work with operator space. It turns out that every vector lattice itself is directed. Of course, because any two elements have the supremum as common upper bound. And you can show that the space being directed is equivalent to the cone being generating, meaning that for any element can be written as a difference of two positive elements. So it turns out that the space of linear operators is itself not directed in general, but you can force it to be directed by only considering those linear operators, which are the difference of two positive operators. But even if you do that, you don't obtain a vector lattice in them. And now comes new figure on the playing field, Van Haandel, and he observed that often for ordered vector spaces, there is still a nice embedding into a vector lattice. And so the idea is to study these nice ordered vector spaces via these embeddings and use basically vector lattice theory in order to study these so-called nice ordered vector spaces. And what I mean by nice vector space has a different name. We call them pre-Riesz space. So ordered vector space or the pre-Riesz space, if we can find a vector lattice with, say, y and a bipositive linear map I from your pre-Riesz space into a vector lattice, such that the image is order dense, meaning that any element in your ambient vector lattice space is the infimum of all elements in I of x, which are larger. We call this such a pair consisting of this ambient vector lattice and the embedding a vector lattice cover. And sometimes we need the smallest vector lattice cover, which we then call the Riesz completion. And it turns out the Riesz completion is very nice and, for example, unique up to order isomorphism. Now some examples. First class of Riesz spaces are, of course, vector lattices, because every vector lattice can be order densely embedded into itself. And this already gives you many examples, like, for example, the Euclidean space with the standard cone, where the order is defined component-wise, or the space of continuous functions with the standard order, so where the order is defined point-wise, or, for example, LP spaces with a point-wise almost everywhere order. But there are many more examples, because it turns out if your space is Archimedean, so for any two elements, x and y, it's true that if nx is less than y for all natural numbers n, then your element x must already be positive. And if your space is directed, then this space is already a pre-Riesz space, and you can also show that these pre-Riesz spaces are necessarily always directed. And it turns out these are very weak properties. As for example, Archimedicity is something that is true for basically all function spaces. And so whenever you have a directed function space, like the space of n times continuously differentiable functions, the space of all polynomials of some fixed degree, or the space of all polynomials, or, for example, the space of the so-called regular operators with directed domain and Archimedean codomain, these are all Archimedean and directed, and therefore pre-Riesz spaces, and therefore enable us to have this nice embedding into a vector. Now I want to give you one more example class. These are these order unit spaces. An order unit is simply an element in your cone, non-zero element, such that every element in your ordered vector space can be basically catched by some multiple of these order units, meaning that your element x is contained between minus lambda times the order unit and lambda the order unit for some positive scalar lambda. And it turns out, if you have an order unit, then your space is automatically directed. And what you can do is, if your space is Archimedean, you can define a norm, which maps any element x to the smallest lambda, which catches basically your element x. And this ordered norm space is then called an order unit space. And since order unit spaces are Archimedean by assumption and directed because of the presence of the order unit, they are also examples for pre-Riesz spaces. Now I want to explain to you how these order unit spaces look like, at least for finite-dimensional spaces. And here one can show that the space Archimedean isn't only if the cone is closed, And the order units are precisely the interior points of the cone. So this means if your cone is closed and has non-empty interior, you have an order unit space and thus a pre-Riesz space. And this gives you already in finite dimensions many examples of pre-Riesz spaces. You could have a cone which, for example, 3 extreme rays, which is also a lattice cone, a cone with 4 or even more extreme rays, or for example, the circular cone where you have infinitely many extreme rays. And these are all spaces which fall into our theory of pre-Riesz space. Now, let me talk about structure preserve, another class of structure preserving maps. Let's start with Riesz homomorphism. So if you have two vector lattices, then a Riesz homomorphism is a map which preserves the lattice structure. So any primum of any two elements gets mapped to the images or to the primum of the images. So these are the natural structure preserving maps of vector lattices. And there's a way to generalize this notion to pre-Riesz spaces. And one way to describe this is as follows. If you have two pre-Riesz spaces and you take their respective Riesz completions, then a Riesz star homomorphism is any linear map which can be extended to a Riesz homomorphism between the Riesz completions. So if you think of pre-Riesz spaces as ordered in subspaces of vector lattices, then the Riesz star homomorphisms are restrictions of Riesz homomorphisms. And yeah, it also turns out that if you have such a Riesz star homomorphism, then this extension is already uniquely determined, and we even gave it a name and call it the Haandel extension. Now, this is the nice characterization of Riesz star homomorphism, but this uses these so-called vector lattice. But there's also a different way of describing Riesz star homomorphism purely intrinsically. And so for this, I now want to consider these three statements. First one is that your linear map T extends to a Riesz homomorphism between the Riesz completions. So that T is a Riesz star homomorphism as introduced on the last slide. The second one is that for any non-empty finite subset F, it's true that if I take first the set of all upper bounds of F and then the set of all lower bounds and then the image, this set is included in the set where I first take the image and then the upper bounds and then the lower bounds. This is weird, not easy to understand, but turns out this describes this Riesz star homomorphism. And then we also consider the same statement where the same inclusion is true, but for sets with at most 2 elements. Now, it seems like that 2 and 3 should be equivalent by some standard induction. And indeed, Van Haandel, who introduced these Riesz star homomorphisms, thought the same. And he showed that all of these 3 statements are equivalent. But then, a couple of years later, Anke Kalauch, who's sitting here with us, and her colleague Onno have written a book on these pre-Riesz spaces and worked through Van Haandel's original proof. And they realized that Van Haandel made a mistake. And that the proof that statement number 3 implies to this so-called standard induction proof is actually not true, or actually not obvious why it's true. There's a gap in this proof. And since then, it was an open question whether these 2 statements are equivalent. But it turns out that the second statement, where we have an inclusion for non-empty finite sets, is actually the one we need, because this really does give us the extension property of the star homomorphism, which is why they are so useful. And now, a couple more years later, like last year, we realized that in fact, both of these statements, 2 and 3, can happen to be no longer equivalent. There are situations where the inclusion is true for sets with at most 2 elements, but not automatically for non-empty finite sets, which is weird, but which happens. So we gave these kind of linear maps a new name, and we call them Riesz star homomorphisms. And there are some simple properties that you can prove. You can show that every Riesz star homomorphism is already a Riesz star homomorphism, and you can also show that every Riesz star homomorphism is positive. And it turns out that if x and y are vector lattices, then all these notions of these star homomorphisms, multi-star homomorphisms, and Riesz homomorphisms between vector lattices coincide. So these multi-star homomorphisms, exactly as Riesz star homomorphisms, generalize the notion of a Riesz homomorphism to order vector space of the thesis. Now my goal is to basically geometrically characterize these multi-star homomorphisms. And this works as follows. Let's say we start with an order unit space, and now we define a new set sigma, which is the set of all continuous, positive continuous linear functionals, which map our order units to 1. This is a weakly star compact base of your dual cone, and so every element in the dual cone can be uniquely written as some positive multiple of some element in sigma. And we define lambda to be the set of all extreme points in sigma and lambda bar as the weak star closure of lambda. And then Van Haandel showed that out of all the linear functionals in sigma, lambda bar consists entirely of the Riesz star homomorphism. So we know, if you know how your lambda looks like, you know exactly where your Riesz star homomorphisms are to be found. And so our goal was now to find a similar characterization, but for multi-star homomorphisms. And we have found something, and I want to give you a really nice result, which only works for finite-dimensional order unit spaces. And here it turns out that if you take a linear functional in sigma, then this is a multi-star homomorphism, if and only if it is true that if you take any affine hyperplane in sigma, which contains your linear functional, then your linear functional can be written as a convex combination of elements in lambda bar, which are also in your affine hyperplane. The proof is not obvious, and I don't want to give you a proof, but I want to use this characterization now to give you the set of multi-star homomorphisms in one particular example. And this is how our cone, or this is how our example looks like. So now we are considering a 4-dimensional order unit space, which has a cone where the set sigma looks like this. The way where you have these two circles or these two cone faces basically which are glued together in the middle. This is our sigma. Now, how does the lambda bar look like? Well, we have the two extreme points on the far left and on the far right, but we also have the entire circle in the middle. And now let's take some linear functional in the sigma and think about whether this is a multi-star homomorphism. So for example, let's take this function of pi right here, which is somewhere in the middle of this right-hand side cone. And let's take an affine hyperplane, for example, this one, which goes vertically through this functional phi. Now, how does the intersection with lambda bar look like? It's empty. So it's impossible for phi to be a convex combination of elements from lambda bar inside the hyperplane, meaning that this functional is not a multi-star homomorphism. And I hope you can imagine that the same argument works for every single point, except maybe for those that are in the middle of the circle. So let's take a functional inside this disk. And let's take some affine hyperplane. Now this affine hyperplane will intersect lambda bar at this middle circle part. And it turns out that phi is a convex combination of these two intersection points. And this is true for every affine hyperplane that you can choose. So this means that this functional is a multi-star homomorphism. And this gives us the example where this real inclusion is true for sets with at most two elements, but not for arbitrary finite sets. So this means that this shows that multi-star and Riesz star homomorphisms can really differ, contrary to what Van Haandel believed. Yeah, so to summarize, our example, our lambda bar was with 2 points on the far left, on the far right, and the circle. But if you consider the multi-star homomorphisms, you get the entire disk in addition. Yeah, so finally, I also want to give you some more results that you can show using this characterization. The first one is if your set sigma is strictly convex. So for example, if your sigma is a ball, if you have a circular cone, then it turns out that all positive linear functionals are multi-star homomorphisms. So this extreme case can also happen, which is quite weird. What's also quite interesting is if your space is three-dimensional and your sigma is not strictly convex, then the sort of other extreme case happens, meaning that every multi-star homomorphism is already a Riesz-star homomorphism. So in particular, for these three-dimensional spaces, only two situations can happen, meaning that either everything is a multi-star homomorphism or the multi-star homomorphisms are precisely the Riesz-star homomorphism. But we have just seen that in four-dimensional spaces, this does no longer happen. And finally, what's also quite nice, if your lambda is finite, so if you have only finitely many extreme points, then it's also true that every multi-star homomorphism is a Riesz-star homomorphism. So in this case, it is sufficient to take sets with at most two elements. And finally, there are also some questions. First one is, how is the structure of these multi-star homomorphisms for general order unit spaces? The result that I gave you only works for finite dimensional spaces. It's not clear yet how we can nicely geometrically characterize multi-star homomorphisms for, let's say, infinite dimensional order unit spaces. And finally, you can also ask yourself, what happens if we consider linear maps where the inclusion is true for sets with at most n elements for some fixed natural number n? There is a project in Leiden going on with Onno van Haandel and a student who worked on this, and they showed basically that, or they have a counterexample, an example for a linear map which satisfies this condition with sets for at most three elements, but I don't think they do not satisfy this inclusion for sets with at most four elements or something like that. But still also studying this kind of linear maps, I don't know, multi-star homomorphisms of degree n or anything like that, is something that isn't done yet. Yeah, might also be interesting. And that's it. Thank you very much. And then have questions at the end. I think we should do that. Or then we can have a question and answer session. Yeah. Yes, that's fine. I have 18 minutes left. Yeah? Oh, sorry. That's okay. If you go a little bit over the time, okay. Yeah, not a problem because it's university break. Okay. So there's no real issue. Relax. Yes. Okay. So yeah, because there are no lectures after. So. All right, can I start? I also want to thank Bruce and Wenchi for inviting us here, and also NITheCS for organizing the whole seminar. It's a pleasure to be here in Johannesburg and present a little part of my PhD thesis. And I want to follow Florian and also tell you things about results concerning pre-Riesz spaces, but I'll try to keep the order structure just the minimum, and really want to have this accessible for people knowing some calculus. Knowing continuous functions might be enough for the talk. And the motivation comes from vector lattice theory. So we begin with some positive results. And Florian already explained to you what a vector lattice is, ordered vector space with a lattice structure. And I also want to have another structure here, namely the algebraic structure. So we want to have the vector lattice equipped with some associative multiplication and should be compatible
interesting, but there is not enough structure to really prove meaningful results. So there are three more, cases with more structure, and the most studied one of the three, or the most well-known lattice ordered algebra, is the so-called F algebra. And here is a concept which Florian didn't explain, so I want to quickly tell you what this jointness means in a vector lattice. One can see the blackboard. So if I'm in a vector lattice, then two elements are disjoint if and only if I take the modulus, which is kind of the absolute value, and then the infimum, this should be 0. It's now a very lattice definition, but if we think in some field space, just continuous functions, and I have two, let's say, functions f and g, then they're disjoint if and only if the product of the two is 0 at every point. So that they kind of have disjoint support. So if you don't know lattice structure, you can always think of continuous functions, and they're disjoint, that basically means product of 0 at every point. So they have disjoint support. And what an F algebra is now is that if I have two disjoint elements, and I multiply one of the two elements with another element, then this should preserve the disjointness. And this suppose for every positive, for every connection of three positive elements. And this now gives you lots of structure. F algebras are very well investigated, very nice algebras. You can prove lots of things. And they have two distortions which also appear naturally when you study F algebra. They have a little less structure, so they're less strong. So every F algebra is a D algebra and it's almost F algebra. And how are those defined? In a D algebra, the multiplication needs to be compatible with the supremum or with the lattice structure. So if I have some supremum, if I multiply with a positive element from left to right, then we should commute with the supremum. And in an almost F algebra, we again have this disjointness property. And if positive elements are disjoint, then the product should be 0. So those are two kind of distortions of F algebra. So every F algebra satisfies the two properties on the bottom, but not conversely, and the two on the bottom are also not related in general. And we are looking at those kind of lattice ordered algebras, and we realized that behind those associative multiplications simply lie some special bilinear maps, which are also structure preserving. And in the case of F algebra, those maps are the multiplication maps are just positive by homomorphisms. If you don't know the name, I will tell you later what it exactly means. For D algebra, multiplication is a bi-Riesz homomorphism, and for the almost F algebra, multiplication of positive force homomorphisms. And the whole goal of my PhD thesis was now, maybe one can generalize those kind of algebras in pre-Riesz space. So maybe we can get rid of the lattice structure and do everything in pre-Riesz space. And then we realized that those are basically just kind of bilinear maps, which are structure preserving. It's a good starting point for this kind of algebraic investigation, and pre-Riesz space would be to investigate those kind of bilinear maps. So Florian already told you how one could generalize bi-Riesz homomorphisms to pre-Riesz spaces by using those kind of bi-Riesz star homomorphisms. And this disjointness can also be done in pre-Riesz spaces. There's an intrinsic definition, but one could also use the vector lattice cover to define disjointness. So if I have a pre-Riesz space, then we know, let's call it X, and we know it can be embedded in some vector lattice phi. We usually call it I, and we can just say in X that two elements are disjoint if and only if the images are disjoint in the vector lattice. So there's some natural disjointness in pre-Riesz spaces by using the disjointness in the vector lattice. So we can also use disjointness to define those kind of maps. And because pre-Riesz spaces are very complicated in general, because we really need the vector lattice cover to understand what's going on, it's always a good starting point to just consider spaces of continuous functions. Because there the order is nice and the disjointness is nice, everything is quite That's easy compared to the general case. And for the vector level case, those maps I showed you are completely understood. They are characterized and properties using this representation and quite easy. So this case we have the space of continuous functions and some output space, and then the multiplication can be given in both spaces. So in the S algebra, you have the multiplication simply the standard multiplication, only by some algebra. So the S algebra is standard multiplication basically. And for D algebra, it's almost the same, but the argument in the functions can be kind of twisted around by map alpha 1 and alpha 2 on the output space. So also called weighted composition operator. And the almost F algebra case is a little bit different. It looks weird in the beginning because the product evaluates at any point is given by an integral with respect to some measure which is dependent on the argument. So for every multiplication you have, basically get a family of positive measures that this multiplication can be given. So both representations are already quite old, and now my question is, how can this be generalized? The basis of continuous functions which are not less. Then why are those kind of spaces interesting? Florian already talked to you about ordinary spaces. And one can show using this lambda bar, if you remember, that all unit spaces are exactly the ordered subspace of some space of continuous functions. So it's not only that I want to consider spaces of continuous functions because they're easy, but because they already kind of cover a very huge class space in the ordinary space. That's why here I'm going to focus on ordered subspace. These functions, but have in mind with this we already have all the unit space covered as well. But from now on only continuous functions, so maybe it's a bit easier for you to follow. Okay, let's begin with the first case. I want to start with the almost extra case, and now we go from the lattices to trees. Okay, first we should define how it looks like, but it's exactly the same as the second case. Now we have some TU Dresden, which are the partial or vector spaces, and we have some bilinear map, and we call it also symmetric for positive elements. This jointness implies that the bilinear map evaluated that those elements is 0. But now we have some problem why, or we can see why Friedrich spaces or partial or vector spaces are more difficult than vector lattices. So if we consider the space of all polynomials, standard interval 0, 1, then there are actually no non-trivial pairs of different elements. You recall the definition for a space of continuous functions. The product should be 0 in every point, and this of course cannot work with polynomials, except one of the polynomials is 0. So in this case, any bilinear map is already of symmetric kind of order, right? And we cannot really expect that something is going to happen. Right? So we need some more assumptions on our spaces that we can get some results. And we found some property already a few years ago, which seems to be the right one to get enough disjoint elements that the definition actually get us something. And this property we call ST for some subspace of space of continuous functions, which is short for separation by disjoint elements. And it just means that if I have two distinct points from my topological space, then I need to find two positive elements which are disjoint, such that the one function is positive in the first point and the other function is positive in the second point. And this property kind of gives you some generalization of the lemma of Horizon, or it's used in a similar manner, the proof that you can separate points with functions which are disjoint. Some examples for spaces which satisfy this property are the states of continuously differentiable functions, any degree. And it's been proved that they can do that because they contain the smooth functions and the an example for a space which does not satisfy a C, which is maybe not distributed as polynomial. It's the Namioka space. It always seems a little bit constructed. And I actually have no idea where it comes up naturally, but it's a very good space to find counterexamples for various statements. And what is the space? I take functions on the interval -1, which are continuous, and if you evaluate it in 0, then it should be the average of the evaluations at -1 and 1. And one can easily convince, you can easily convince yourself that the point 0 and -1 or 0 and 1 cannot be separated by 1.
Make a remark here that this intersection of the kernel of function and this next this
Okay, so we have spaces which have SD and space which does not have SD. And before I show you my representation result, quick reminder how it looks in the vector lattice space. We have here the bilinear map on the whole space of continuous functions. And this space is also symmetric, and this map is also symmetric if we get this family of measures which are positive, such that at each point we get this integral representation with respect to this. That was done over 40 years ago, and now the question is, does it still hold in a partial vector space case? And then yes, but we have to assume some additional conditions. So in this case, we have the subspaces of the continuous function, but the domain now has to satisfy the property as B. It still needs to be majorizing in the space of continuous functions. It means that above every continuous function, I need to find limits. Then, as every positive bilinear map is also symmetric, this is only is, I guess, like everything works the same, except I need to satisfy this. And it turns out that if we assume that every orthosymmetric map has this kind of representation, then already follows that the space has a C. That C is actually necessary to get this kind of representation. So it seems that this property is exactly what we need to get enough disjoint elements that everything works out. Okay, now we can check if this representation maybe gives us some immediate properties. And as always, the first glance at what is going on in vector lattices. If you have Archimedean vector lattices B and F and some positive orthosymmetric map, then this map is actually always symmetric. So it's almost as algebra I showed you in the beginning. I always mutative, that's Archimedean. And the map also is positively semi-definite. It means that if I plug in the same element twice, then it's positive, even if the element itself is positive. And then in terms of algebra, this means that it has positive square. Yeah, exactly. And then if we are in the setting I showed you before, so we have exactly the conditions from the representation theorem to get the same property. And used by the representation, writing a map is still symmetric, semi-definite, and you can use integral representation to find an extension to the whole space. Yeah, if we don't have SD, it doesn't work, of course. Then take again the space of polynomials, which has not SD, and we now consider some positive bilinear map defined like this. So we put in two polynomials, values at some point, and what we get is that evaluating the first polynomial in 0 and the second one in P. And this is of course also symmetric, because on polynomials everything is also symmetric. But yeah, I can check easily that it's not symmetric. So for SD everything works out fine, and without SD everything is ruined. Okay. Let's go to the second case. We go to the bottom here, the algebra, and we said that the multiplication here is just the Riesz homomorphism, right? say here from the left, with positive elements, then this distribute over the primum. So this is exactly Riesz homomorphism. So the bilinear map we should consider here in the partial vector space case are the bi-Riesz star homomorphisms. Let's define what that is. We then have some partial order vector spaces x1, x2, and y, and some bilinear map. And we call this a bi-Riesz star homomorphism. If for any element, any positive element, if we put in the first or the second component of our bilinear map and fix this linear map, then those have to be Riesz star homomorphisms. That's the usual definition you do when you have something by structure preserving and you fix one component, and then what you can put as uplift is just the linear version of that. And Riesz star homomorphisms are this what Florian explained to you. I hope you recall those are the ones which can be extended from pre-Riesz to the vector that it covers or Riesz completion. And before I can go to the representation on continuous functions, we need to have a look at a more general order structure result. We here have vector lattices E1 and E2, and the real valued bi-Riesz homomorphism from the Cartesian product of E1 and E2. And we can always factorize this bi-Riesz homomorphism into two revalued Riesz. So we get some Riesz homomorphism sigma on E1 and tau on E2, and my bilinear map can then be written as a product of those two. Just remember the representation on the continuous functions have already looked a little bit at the product of some map. And what I could show is that the same holds for pre-Riesz spaces if we consider bi-Riesz star homomorphism. So we have to replace vector lattice by Cayley space and bi-Riesz by the star homomorphism. And then we get two Riesz star homomorphisms. And one might expect that this is obvious, kind of, because these star homomorphisms can be extended, right? And then I get the Riesz homomorphism here, and then restrict them and get the Riesz star homomorphism here. But actually, it's not trivial, because for bi-Riesz star homomorphisms, we don't have any extensions. And it's also not easy to get any generalization of the linear result just doing a bilinear doesn't work. Much more complicated. Only for very special cases, I proved some extension, but in general, we don't know. So the proof is elementary. You really have to work with it, not the extension. Okay, but we can use this factorization to get the result for continuous functions. Because for real valued Riesz star homomorphisms, we know that they're just the pointer values. So we have now ordered in subspace of continuous functions and the real valued by Riesz star homomorphism. And we get some positive scalar and 2 points from the topological spaces. Such that my bilinear map is the product of the point evaluation. This again already looks very much like the representation we get in a general case. But before I show you this, again, quick reminder, the vector lattice case. There's some positive bilinear maps on the space of continuous functions. This is the bi-Riesz homomorphism that we get some positive wave function and two continuous maps on our space. That will only be continuous, of course, on the set where our wave is strictly positive. Then the multiplication is the wave composition. Okay, and now we have a look at the partial vector space case. Now we don't have the whole space, but only ordered in subspaces. Let's take some positive bilinear map. And we use some very mild conditions on our space x1 and x2, some very mild separation properties, nothing major. Then we get exactly the same truth. This of course follows from the representation for the real values homomorphisms by kind of patching together all the find evaluations we get to our alpha 1 and our alpha 2 and our scalars R in the for the real David space we patch together to our wave function. It's very technical to show that those are then continuous and everything works out. But yeah, that's technicality. And then we get this kind of space. Okay, so we have two cases in the back. Let's have a look at the third case. The most important lattice ordered algebra, the F algebra, now generalized partial. So we can have this joint here, multiply by an element, then this joint is repeated. So only if we imply multiply one of the two elements, the positive element. So let's define again the underlying map. First, we do the linear case. We have some partial vector space in the linear map, and we call it band preserving. Comes from the notion of band in ordered vector space. Not too important here, but we need to satisfy that if I have two different elements and I apply my P to one of the two elements, then the disjoint is reversed. That's exactly what we had before, the multiplication by positive element would be our P here. And if this map is in addition positive and also band preserving, then we call it positive or homomorphism. And this kind of operator is very well studied in vector lattices. Many nice results, but in partial vector space we don't know much, very little. Because the disjointness is just very complicated. And we define again a bi-version of this operator. It's a partial order vector space, and we call it positive bi-homomorphism. Again, if it's one of the arguments with a positive element, then the result is positive homomorphism. Very similar. And what was shown in the motivational scheme is that if I have a bi or homomorphism on a vector level, then it should always be obviously symmetric. And any F algebra is forms F algebra. This is what this statement here says. And in partial vector spaces, we get exactly the same. That works with the disjointness, and everything works the same way as in the vector level. And let's have a look at the vector lattice case of the representation again. I have some positive bilinear map in the space of continuous functions. And then this map is a positive bi-homomorphism. It's just the basic version of this. Okay. Let's see if it still works in partial vector spaces. Big surprise. The definition of the map involves disjointness. Right? So of course, in this case, you also need to property. But without SD, you have to look at the space of the longest again, any map is positive. Interesting, but if we assume SD again for us other than subspace, then we get exactly the same representation. So the property SD seems to be really important. Now we receive the same representation in the end. And to summarize everything, we get a similar scheme as for the vector lattice case, but this time we just have an ordered in subspace of the continuous function. And we get the same representation as in the vector space, except of course for the bi-homomorphism and the orthosymmetric map we need to set C. Without a C, no hope to get anything like this. And yeah, I mean, at least for this case, we have kind of a complete picture of what is happening. But now the natural question is, how does it work for generalization? Right? Yeah, the disjointness is kind of a mystery sometimes. And it would be good to have an analog of SD for this somehow. And we haven't found anything which works in the same way, which can be used to prove results like this, or even relay the to other structures. So different things can be so fast and yeah, that's everything I wanted to tell you. Thanks a lot, and here are my references, and thanks for listening.
Are there questions from the audience in the room? You did a whole lot of the work in terms of CA. What happens when you step outside of that?
Yeah, that's the problem. There, we don't know much, to be honest. So, yeah, as I told said before, the FD property is very important for the two cases where we need disjointness, and also for reach-down homomorphism. We don't really have any representation or anything tangible. Yeah, it's very hard. I mean, there are some cases there also results in zero of some locally compact Hausdorff space, but it's also still open.
I'd like to know how this would be applied in real life.
Yeah, that's always the question. I mean, this kind of thing. I mean, S-algebras are used in many ways. I mean, they're applied in the work of Bruce and Vinci, of course, generalizing this stochastic in Riesz spaces. I mean, it's still not really real-world application right now. But I mean, I know that S-algebras are also used in partial differential equations sometimes. And I mean, this is just very basic work right now. It's not really clear how it's going to be applied. There are also links to economics, but I don't really know how the links look like. Yeah, our motivation is mostly intrinsic. But if the experts in positivity know anything more on applications, I would be happy to have some position.
Pre-Riesz spaces come up quite naturally from studying vector lattices. If you start studying the maps between vector lattices, the linear maps between them. Unless you have extra conditions, the those operator spaces don't form vector lattices. They only form pre-Riesz. They don't have them, even though you start off with vector. So all your LP spaces are vector. A whole lot of the things that you look at, pretty much all of your analysis you see at the end of fourth year lives in the world of vector. But as soon as you start looking at operators between those don't form vector. They don't, they've lost some of that piece. That answer your question.
Just one comment. I mean, when you think of real life applications, and the fundamental class of the dynamic system, you have project of model is and some people happen to engineers do this. And the big class of the dynamic systems are so-called positive dynamic systems. So you start with cone, and then the trajectory develops in the cone over time. You have so-called positive dynamic systems, and they appear in biology. You have a positive number of bacteria and want to know how they develop. They appear in economy. You have a positive number of goods, etc., etc. They appear everywhere. And the theory of the operators on whole gives you an expected theory, and an expected theory, and field theory synthetase. This is a nice description what happens on the long run in the dynamic system. And what we do here is cross structure theory and basis of the whole issue. But the applications are outside everywhere. So
Yeah.
I have a question, but before I ask, I'll just add to what you said. For dynamical systems, I'm answering it now. For dynamical systems, with respect to rails, I know, I think I've read somewhere that has something to do with biology, especially with the respiratory system. So it has application in that section. You try to look for that feedback, just a contact. Then my question is to the previous speaker. Sorry, I didn't get your name, but I was late. So your results on mild was done in finite dimensional space, and I heard you say that you don't know what happens with infinite dimensional space. But I'm thinking, did you try to consider maybe a Hilbert space, because it has some simple nice structure?
That's actually also right now the conjecture that with the Muller characterization might hold true in Hilbert spaces, because also in our proof, if I remember correctly, we used basically I think projection onto convex depth and something like this. Maybe this still works, but I don't remember if there maybe was something special for finite dimensional spaces that we also use. I would have to look up that. But yeah, it's, I completely agree that maybe there is something we can recover for Hilbert.
I want to check if there are any questions online.
Oh, yeah, maybe you should. I don't want to touch. I just want to also add on the question about the real life application. So in the stochastic process, because we prove the probability theory and the stochastic process is using the order vector lattices. So there is some sort of financial application as well if you go through that route. But obviously that is another route that is different. But this, in terms of application, it's vast. Maybe not directly into sort of apply mathematical type of application, but definitely the basis is there. For
we don't really want to answer it, because then they will merge our two departments.
We are not mathematicians.
Okay, there are a couple of questions in the chat. The first one is... Does the bilinear map for D algebras provide a tensor product on the D algebras? Is there a connection between your bilinear maps there and tensor product?
So we know that the tensor product of D algebras is again a D algebra. That was proved, I think, by Amin Benamon and collaborators. But the question now is if this map provides the tensor product. Not sure if I get the question right. So we know that the tensor product again is the algebra, the Fremlin tensor product of Archimedean vector lattices. It's not providing a tensor product really, but yeah, I hope this answers this question. Okay. And there are two questions regarding the disjointness, right? Because I did it on the blackboard.
Actually three, but
okay.
What is the orthogonality relation? But I think
I guess
that was talked about in the pointwise, where you could do it pointwise.
Yes.
In general, it's a far more complicated problem. If you, but you can give the definition.
I'm not sure if they can see it.
I can.
Apparently not.
I can change to video.
On a blackboard.
Yeah, it's on the blackboard.
I
think on the screen.
And then the other one is again the relationship between.
I'm not sure. Yeah,
it's not very good. We've got lots of shine on the screen.
Yeah, I mean, I can say it again in vector lattices. The disjointness means that maybe I can. Yeah.
Like to build it without disturbing the video system, so that.
I mean, let's just say what it means for positive elements, because for positive elements, we only use it for positive elements. Two positive elements are disjoint in the vector lattice sense, if their infimum is 0. That's basically it. And if you consider this now for space of continuous functions, then this means that they're co-zero sets. So the point where they are non-zero, that they are disjoint. Or the product of those two functions is 0 at every point. But, yeah, okay. Kind of mirrored, right? I cannot really.
Oh, okay. Okay, sorry. I didn't realize that.
Okay, I hope this helps. I mean, it's also in vector lattice books. I cannot really show you now. I'm sorry.
And the last one was about the D algebras and tensor products. Relationship between product, your bilinear map and tensor products there as well. So that there was yet another.
But that's the same question, right?
It is, yes,
Okay.
but it was posed by two different people.
Okay, I see. People are interested in tensor products.
Yeah.
Good.
And
Right.
then if there are no further questions, I
We should close.
think we should
now.
thank our two speakers.
Yeah. Thank you.
And we thank our online audience for joining us.
Advertise.
And tomorrow, Professor, Docent Professor Dr. Anke Kalauch will be giving a seminar, and that will also be streamed through COE on pre-Riesz spaces and structure preserving operators. Please join us. Again, it's at 10:30 tomorrow, isn't it?
I think so.
10:30. So if you can't join in person, you can join us online through the COE, Center of Excellence link.
Okay.
Sorry?
Downstairs.
It'll be down on the first floor seminar room.
Thank you.
Thank you.
Thank you.
And